All right, let's get started. So in the previous chapter, we talked about the elements of database system. While in this chapter, we'll discuss the steps to be undertaken to design and develop a database-based information system. So this process is called System Development Lifecycle. In this chapter, we'll first distinguish between the system lifecycle, through which all systems must pass, and the system development lifecycle, which is a series of steps involved in creating a new information system. And also, alternatives to the traditional system development lifecycle will also be discussed in this chapter. If you can recall from the previous discussion in the first chapter, that information systems are designed to provide useful information for decision making. So first, we will examine the driving forces behind new information system development. Next, we will consider the system's life cycle, which describe the stages through which all systems pass. And finally, we will discuss the system's development life cycle, which comprises the steps required to actually develop information system. So first of all, let's see the motivation for systems change, or why do we need to develop a new system? The motivation for system change, either the customer development of new information system or the acquisition of a new software package. These can originate in a number of ways. Users at various levels in the organization can successfully behind new system development or significant modification to existing systems. Deficiencies in existing systems, such as information needs to go unmet, lack of timeliness of information, or they have difficulty in using the system. Well, these are the examples of user complaints that spur the development of new system. If the purpose of information system is to provide information useful for decision making, and if existing systems are falling in that regards, then new solution is to develop a new system or significantly modify the existing system on a number of factors. Changes in a competitive, legal, or regulatory environment are examples of factors that can cause user needs to change. In addition to users, information systems professionals, accountants, and perhaps even customers or suppliers can follow the development of new information system. For example, information system professionals, for that matter, may recommend new systems or system modifications to take advantage of new technologies. Many companies have information systems professionals who are responsible for monitoring development in information technology to take advantage of new technologies as soon as they mature. The university and use of the World Wide Web is spurring a number of companies to seriously investigate doing business on the web. It is estimated that a number of companies using the web for electronic commerce will mushroom over the next year or two. This move towards electronic commerce will undoubtedly necessitate modification, perhaps major ones, to existing systems. Competitive forces may also cause an organization to consider the development of new systems. You may have noticed that most new innovative business practices introduced in the marketplace are soon copied by the competitors of the innovative companies. For example, Federal Express provided its customer with a package tracking service on their website. Responding to this innovation, UPS followed this approach very soon. And IBM was the first company to offer a track pointing device on their ThinkPad line of notebook computers. But a number of other notebook manufacturers, such as Toshiba, were quickly to follow the IBM's lead. Well, these are two examples of the competitive forces that drive the IT system, the information system to develop in a develop to a new trend in a company. So this slide shows the system life cycle. All systems, not just information systems, should go through a series of stages from the time they come into existence to the time they cease to exist. Human beings are one example of such a system that goes through the stages of birth, childhood, adulthood, and old age. We can probably relate this cycle to many systems such as automobiles, houses, and of course, information system. This four-stage process of creation, startup, maturity, and decline is referred to as the system life cycle. The first stage, creation. This stage comprises all the steps necessary to actually develop the information system. The system development lifecycle that we will discuss later in this chapter occurs during the creation stage of the system lifecycle. Upon completion of system development steps, the information system is implemented and thereby moves to the second phase in the system lifecycle, startup. The startup stage, typically the shortest stage in the system lifecycle, comprises the initial use periods when errors will be corrected and the system will likely be changed to better meet the user's needs. The third stage, maturity, is typically the longest period in the system's lifecycle, where it is considered a stable system operating smoothly, with only minor and routine usefulness. Users' needs, the environment, and technology have changed significantly, and rather than performing major surgery to the existing system, it is preferably to simply start a new building of a new system. A new system will again go through the 4 stages of this system lifecycle. Well, in the previous chapter, we introduced system lifecycle, but now only one word as extra. We will introduce system development lifecycle. Well, you guys will be working as future system development people, maybe in your future works. So it is necessary for you to know how to develop a new system. Well, in the early days of computing, in 1950s or early 1960s, applications were developed as needed with little planning. More often than not, haphazard systems developments resulted in erroneous applications that were delivered behind schedule and over budget. As a potential solution, the systems development lifecycle approach was proposed in late 1960s as a planned approach to developing a new information system. So, system development lifecycle process was conceptualized as a response to systems projects that were invariably behind schedule and considerably more expensive than anticipated. What are the consequences of a poorly planned and executed system development process? Let's examine the questions in the context of implementation of ERP system. which virtually all the Fortune 1000 companies rely on for their resource transaction processing. Contemporary ERP systems, such as SAP, take years to implement and cost several millions of dollars. When properly executed, the ERP system may be very useful for the business, but missteps in one or more steps in the system development life cycle process can be you know disasters for the company. For example, Hershey's was in the midst of the ERP implementation in the middle of 1990s. Unfortunately, due to problems in configuration of the Hershey's SAP system, it was unable to deliver Hershey's chocolates to the stores during Hollywood in that year. The net result was about $100 million in lost sales, and the company's stock fell by 8% as a consequence. So this story underscores the importance of employing a planned approach to system development. So we need to pay very close attention to detail at every step. In addition to employing a planned approach to developing individual systems, organizations are realizing that an overall master plan of information system is essential. Ideally, the information system plan should be aligned with organization's strategic business plan. Information systems play a critical role in the success or failure of a business and should be seen as integral part of an organization's business plan. In addition, organizations today are increasingly seeking to exploit information technology to obtain a competitive edge in the marketplace. Well, there are 5 stages in the system development life cycle. First, system analysis. 2, system design. 3, system development. 4, system implementation. And finally, system operations and maintenance. This process begins with an analysis of the problems and ends with smoothly operating systems in place. There may be a slight variation of these 5 stages in practice. For example, the development and implementation stages may be collapsed into one stage, or the design and development stages might be classified together. The 5 stages are sequential, with the output from each stage feeding into the next stage. But it is also possible that findings from one stage can be feedback to the earlier stage to refine the output from the previous stage. So these slides shown here is referred to as a waterfall model of systems development. These 5 steps will be discussed in detail in this chapter. The analysis stage, the first stage. This stage involves understanding the existing system and its shortcomings. The design stage involves developing data and process models for the proposed system. The development stage involves actually creating the data structure and programming. The implementation stage involves converting from the old to new system. And finally, the operating and maintenance stage involves using the new system and fine-tuning it. So in this chapter, we will present an overview of these 5 steps and provide some general guidelines for each step. We will steer clear of a very detailed discussion of systems analysis, implementation, and operation and maintenance. But system design and development can benefit from application of specific guidelines, especially for business context. And these guidelines will be discussed in the next chapter. Well, first of all, let's see system analysis. Well, system analysis can be undertaken either to examine all aspects of an existing information system or to design a new database system. In either case, systems analysis consists of the following steps. First, requirements analysis. Two, secondly, a system survey, and lastly, feasibility analysis. So let's see each one of them in detail, one by one. First, requirement analysis. Probably it is the most critical step in system analysis. Systems analysis employ a number of techniques to understand system requirements and elicit specifications for users. The objective is to understand what tasks users perform and hence what information they need to perform these tasks. Well, interviews, questionnaires, and observations of activity, and examine existing documents are the main techniques that can be used for requirements analysis. Each of these techniques has advantages and drawbacks. The interactive nature of interviews is beneficial for both users and interviewers. The user can ask for clarification on questions, and the interviewers can ask relevant questions based on the user's answers to previous questions. But conducting interviews is not cost effective when many users are involved. Also, the unstructured nature of interviews may make it difficult to analyze data obtained from different users who were likely asked very different questions. Finally, users may not provide truthful answers to questions posed. Despite these drawbacks, user interviews are probably the most commonly used technique for requirement analysis. And next, the next approach is questionnaire. Questionnaire are very good for obtaining data from a large number of users and can be structured to obtain uniform answers from users. Another advantage of questionnaire is anonymity, which means users can supply more candid answers when their identities are not revealed. But because of anonymity, some users may fail to respond to questionnaires precisely, and items on questionnaires are subject to misinterpretation unless great care is taken in designing the questionnaire structure. Questionnaires response questionnaires may not necessarily be truthful in that case. Observation of activities. Well, this is another technique used to understand users' needs. This technique has the advantage of objectivity. The the analyst actually observes on site what users do rather than users simply telling them what they do. But observation can be extremely time consuming and it is an expensive technique. In addition, people tend to act differently when they know that they are being observed. So, what we observe may not accurately reflect the reality. The final technique involves examining the existing documents and reports. Like observation, this technique is relatively unbiased because the analyst is not relying on the user's description of what they do. Instead, to the contents of current documents are inadequate to meeting the user's needs. Merely examining the documents and reports is insufficient means of understanding users' requirements. An optimal approach is to use multiple techniques. We can combine interviews, questionnaires, and observations together. System survey. The next step in system analysis is system survey. It is used in the context of an existing information system. Excuse me. The main purpose of system survey is to determine the strength and weakness of existing information system. The technique involves obtaining feedback of users and developers about various aspects of systems. In particular, the survey focuses on the extent to which the system meets users' needs. System developers provide input regarding the maintainability of the system and perhaps the performance of system. A possible outcome of a system survey is the finding that users are not aware of the system's capabilities. Problems identified by users may be due to their lack of understanding of how to use features that are already programmed in the system. The solutions to such problem is simply to train the users rather than to build a new system. Feasibility analysis. Since we have analyzed the requirements and surveyed the existing system, it is possible now for system analysis to develop some very preliminary estimates about the new system or the changes to the existing system. Well, at this stage, it is now necessary to determine whether the new system or the proposed system changes is feasible. Feasibility analysis is the third step in system analysis process. There are a number of aspects of feasibility analysis. Economic feasibility addresses the question of whether the benefits of system outweighs its cost. Economic feasibility is an issue that is revisited through the system development lifecycle. If at any stage in the system development lifecycle, it becomes apparent that the benefits will not outweigh the cost of developing and using the system, the project would be abandoned. While the costs of new systems are relatively easy to quantify, the benefits are much harder to associate with dollars and cents. For example, it's very difficult to associate a monetary value to the benefits of being able to respond to customers' queries faster. Both outflows and inflows associated with the new system must be estimated over the life of the system. System design. The main focus of the system design stage is to develop a model of the proposed system. First, logical data and process models are developed, after which the logical models are converted to DBMS-specific physical models. Well, in the next chapter, we will discuss the details of the logical modeling approach for designing database-driven systems. The specific steps in system design includes first, logical data and process modeling. Second, model integration. Third, translating logical data and process models to physical systems. And last, the documentation of models, as well as feasibility analysis. Well, here, the first and second steps comprise logical design, whereas step 3 and step 4 comprise physical design. Well, the last step is simply an ongoing activity that occurs during all phases of the system development lifecycle. The first step in the system design process is logical design, which consists of logical data modeling and logical process modeling. Logical data modeling is a comprehensive structured model that is representation of data items of relevance to system users. Logical data modeling is also called conceptual data modeling, since the goal is to design a system at a conceptual level. A popular tool for conceptual data modeling is the ER diagram. ER diagram is called entity relationship diagram. This technique, the ER technique, will be discussed in detail in next chapter. But let's briefly explore the ER technique here to facilitate our discussion of the system design process. Entity relationship or ER diagram uses rectangles to represent entities and the diamonds to represent relationships. Again, this is very important. In entity relationship diagram, it uses rectangles to represent entities and the diamonds to represent relationships, where entities are simply the objects of interest in demand being modeled. In an educational institution, the examples here, the courses, students, and events such as registration are all entities. Associations between entities are relationships, as known in the simple ER diagram. 4 is the relationship that links the courses entity with the registration entity. And by is the relationship between registrations and students. So this ER diagram would be read as registrations for courses are done by students. And in the next chapter, we will discuss an extended version of basic ER diagram, which is called EER, that is Extended Entity Relationship Diagram. In the EER model, in addition to showing the entities and the relationships between them, it also shows the attributes for each entity and relationship. The primary key in the entity and relationships is also depicted in the EER diagram. In addition, in the EER diagram, it shows the cardinality, where the participation of relationships is optional and mandatory. It's shown in EER diagram. Okay, well, we will discuss this in later chapter. Although logical modeling in general and ER modeling in particular is independent of any specific type of database model, ER modeling lends itself very well to the design of relational database. In the next chapter, we will explore in detail the methodologies for constructing ER diagram in business context. The second aspect of logical modeling is logical process modeling, while data modeling is oriented toward the data item of interest. Process modeling focuses on the procedures that modify data items. A commonly used tool for process modeling is data flow diagram or DFD diagram. While the logical data model focuses on the various data items and how they relate to one another, the DFD model focuses on the logical flow of data in the system. The DFD technique will also be discussed in greater detail in the next chapter. So here we just simply get to know the basics of DFD model. In DFD model, only four symbols are used. It uses squares to depict external entities, circles to represent process, arrows to represent data flows, and open-ended rectangles to depict data stores. Physical details, such as the number of copies of documents or the specific fields in the file that are updated, are ignored. A simple DFT diagram for a registration process is shown here. Students is the external entity. Registration process is the process. Registration and courses are the two stores of data. And the labeled arrows indicate the flow of data. The logical modeling process described here is commonly used today to develop the business information system. A logical data model is developed employing the modeling technique, and a set of logical process models are developed using DFD. Well, now we get to the physical design. The previously discussed logical design model aids the users in understanding the proposed system, while the physical model or physical design contains specifics of relevance to a particular database management system. The physical design process begins with the translation of a logical model to a physical model and commutes with the documentation of the physical model. So the first step in the physical design process is the translation of logical model to a physical model. In this step, system designers convert the ER and DFD diagrams into solutions that can be directly implemented in the relational DBMS. Specifically, we mean that ER and DFD diagrams will be mapped to tables and forms in the DBMS, well, such as access. During the system design stage, table structures, their primary case and foreign case are determined. The ER diagram should also provide details such as the attributes for entities. Entity attributes map to fields on the table. The process of creating detailed ER diagram and mapping ER diagram to table in a relational database will be discussed in the next chapter, physical design chapter. Inputs and reports formats will also be designed in this stage. The DFDs provide some of the details necessary to determine the screen contents of input forms and reports. Since the system's design stage is a precursor to the system implementation stage, the various tasks performed during system design are intended to facilitate the implementation stage. As noted on feasibility, if you can recall that feasibility analysis is an ongoing process which is revisited at each stage in the system development lifecycle process. At the conclusion of the system design, the designers must make the call whether the design of they have created passed the feasibility test. If the design is deemed not feasible, then the project must be abandoned. At each step in the system design process, and in fact throughout the SDLC, which means System Development Lifecycle, SDLC process, it is critical to document what was found and what was done. Logical and physical data and process models must be thoroughly documented, for it is the documentation that will be relied upon during the subsequent development and implementation stages. In addition to the ER and DFD diagrams, the mapping between the two performed during model integration and the resulting DBMS specific physical models must be fully documented. In a sense, this documentation is aimed at creating detailed written steps in the system development lifecycle. There may be a tendency for analysts and designers to view documentation as a necessary evil because and put it off until the very end. The problem with this approach is that memories are not perfect. It may be difficult or virtually impossible for the designers to remember every single detail about steps implemented several weeks or months ago. The best practice is to document activities on an ongoing process. Well, as we will discuss in later chapter, automated tools for system development lifecycle automatically generate a good base of the documentation. Feasibility analysis was first conducted during the system analysis stage, with the detailed database system design having been granted to the system design stage. The feasibility questions are revisited. The detailed design permits a more accurate estimate of the cost of building a new system. The potential benefits are also possibly easier to envision and quantify with the completion of the detailed design. So, the feasibility question is again asked, like, will the benefits of the system overweigh the cost of building the system? Technical feasibility is also easier to evaluate upon completion of the detailed physical model. It is possible that currently available technology may be inadequate to fully implement the detailed design. If it appears that at the conclusion of the system design stage that the cost would outweigh the benefits, or the system is not technically feasible, then the system development projects should be abandoned. If the benefits appear to exceed the cost and there are no technical handles, the project process to the system development and the implementation stage. The various steps in the system design stage are summarized. So the next stage is system development. So having arrived at a satisfactory design for the system, the next step is actually to develop it. The next chapter provides details of the development process of the database based information system. But here, let me tell you that system development compromises the 5 steps. 1. Creation of data structure. 2. Detailed programming. 3. Testing. 4. User training. And lastly, of course, feasibility analysis. Whereas the design phase aimed at creating logical and physical data and process models. Development, system development is aimed at creating a working information system. In other words, this stage is aimed at creating a functional relational DBMS based on specification generated during the system design stage. The first step in the system development is the creation of data structures. For our focus on relational database system, this step refers to the creation of tables using the DBMS data definition language or environments. Table names are adopted from the entity and relation names identified on the ER diagram. A well-specified ER diagram can greatly simplify the development process. Also, it should be apparent that the ER modeling process lends itself well to relational database implementation. In addition to creating tables, the database designer would also use DBMS facilities to enforce entity and referential integrity, as we discussed in the early chapter. Table level controls, which may not be apparent in the ER diagram, but may be identified during the system analysis stage, where these stages are defined using validation rules. A detailed programming required to implement the design conceived during the system design stage is one of the major tasks undertaken during the system development stage. The initial step in the system development, that is, the creation of data structure, involves relatively straightforward tasks of creating tables, designing key fields, establishing relationships between tables, enforcing entity and referential integrity, and defining validation rules. The detailed programming step involves the significantly more complex task of creating interactive forms with buttons and executes a series of tasks when clicked. In Microsoft Access, interactive forms can be designed with buttons that invoke either access macros or modules written in the VB, Visual Basic programming language. After creation of tables, forms, and perhaps some queries and views as needed, a critical step in the development stage is testing. As tables, forms, queries, macros, and program modules are created, they are automatically checked for syntax errors. As an example, Microsoft Access will not tell you create two tables with the same name or two fields in a table with the same name. Syntax of macros and VB code is similarly checked instantly. Testing the logic of programs can only be done by running a sample data through the system. Realistic test data should be obtained from users and run through the system. Previously processed data can be used to test the logic programs into the system. As a more thorough test, system testing involves putting the system through the paces in an environment that are closely mirrors the user's live operating environment. It is vital to have the user involved during the testing stage, especially during the acceptance testing. Indeed, user acceptance testing is one of the most critical steps involved in implementing a new system, since the end users are the ones who would be most knowledgeable about the real world scenarios in which the system will be used. Of course, for information system professionals to be well versed in the design and development or relational database system puts them in a unique position. They are not only familiar with the requirements of database-oriented process, but also the capabilities of relational database system. Training. One activity that should begin during the development stage is user training. When converting from a manual to a computer-based system, trainings of users may be a a very daunting task, at least when converting from one computer-based systems to a new system. Basic computer literacy is not an issue to the extent that the new system is radically different from the old one. User procedures may be quite different, and extensive training may be required. Although the new system is still in the development stage. And lastly, feasibility. Upon the completion of system testing, the feasibility question is again revisited. Depending on the test result, it may be determined that the system simply does not adequately meet users' needs, or perhaps the performance under realistic conditions was unsatisfactory. It may be determined that considerable additional investments in hardware or software are required to bring system performance to an acceptable level, and those additional investments may not be deemed cost effective. So it is conceivable that even after 3 steps in the system development lifecycle process, the project could still be abandoned or at least temporarily shut down. So that's all of this class. In the next class, we will continue the discussion of this chapter, starting from system implementation stage. All right, so please let me know if you have any other questions. Or I will see you next week. All right, bye bye.